Ask a reasoning model who Canada's first woman prime minister was, and it may confidently insist there never was one. The answer, Kim Campbell, can already be inside the model. The failure may be access, not storage. Ma and Hewitt test a precise claim. Reasoning models are optimized to think through math and code, but not necessarily to search their own parametric memory. A tiny Q exposes the gap, and reinforcement learning with verifiable answers trains better access. Parametric knowledge is the world knowledge encoded during pre-training. Closed book question answering asks the model to recover it without documents, search, or tools. A wrong answer therefore mixes two possibilities. The fact was never stored, or decoding failed to reach it. The paper proceeds in 2 steps. First, compare normal reasoning with the exact same model, prompted to think step by step. Then train GPT open source 20B on Trivia Q, using only answer correctness, and test whether recall improves elsewhere. Formally, the model samples a reasoning trace from the question, then samples an answer conditioned on both the question and that trace. The trace is not decoration. Forcing it to be empty makes the 3 open models 9 percentage points worse on average. The motivating analogy is spreading activation in human semantic memory. To recall Canberra, a model might activate Australia, major cities, and purpose-built capitals before the answer surfaces. The useful trace need not be a formal proof. It only needs to reach the stored association. The diagnostic has 3 conditions. Direct answering forces an empty thinking span. Default reasoning allows the model to think without a special cue. The cued condition changes only one phrase, think step by step. The appendix confirms this is a remarkably tight intervention. Both prompts demand answer tags, and the only substantive addition is the 4-word reasoning cue. That makes paired performance changes easier to interpret than a large prompt rewrite. Trivia Q and natural questions measure closed-book factual recall. Math is the contrast condition. Current reasoning models have already been heavily optimized for mathematical traces. If the Q merely makes every answer better, it should help all 3. 4 models span 5 billion parameters through GPT 5.2. Exact match is strict. Extracted recall first asks GPT-5 Mini to extract 1 confident answer span, then checks whether a reference appears inside it. That relaxation handles verbose reasoning without rewarding a list of guesses. Q improves extracted recall across both factual datasets, averaging 0.8 points over 8 model dataset comparisons. For GPT open source 20B, Trivia Q arises from 61 to 61. 2 and natural questions from 37 to 32. 0. Small but paired and consistent. Math behaves differently. Q slightly hurts ALMO and does not help GPT OSS or the distilled model. Only GPT 5.2 gains. The interpretation is not that Qs are universally powerful, but that factual access is less saturated by prior reasoning training. The training stage never labels the reasoning trace. It samples a trace and answer, then changes the policy to maximize the scalar reward on the final answer. This is reinforcement learning from verifiable rewards. Correctness supervises the path only through its outcome. The reward has 2 pieces. Exact match earns 1, containing the reference earns 1/2, and a wrong answer earns 0. Malformed answer tags subtract 1/10, encouraging parsable outputs without making format the main objective. For each question, the current policy samples a group of 8 complete trajectories. Every trajectory gets a reward, then its advantage is reward minus the group mean. The update therefore asks which attempts were better than the model's own alternatives on that question. The policy gradient estimator applies that one trajectory advantage to every generated token, corrected by the new-to-old token probability ratio. Because sampling is on policy, those importance ratios stay near 1. The displayed equation omits the reported KL penalty, an underspecified detail worth noting. Training uses an 80-20 split of Trivia QA, Tinker, rank 32 low-rank adaptation, 8 trajectories per group, and 32 groups per batch. Learning rate is 2 times 10 to the -5, the KL coefficient is 0.01, and sequences are capped at 1.028 tokens. Reasoning SFT controls for simply imitating successful chains. The base model generates traces once, incorrect traces are filtered out, and supervised learning copies the remaining 40,000 examples. Unlike online RL, the reasoning distribution cannot adapt as training improves the policy. The appendix matches the baseline carefully. Rank 32 adaptation, batch 32, 8 epochs, and checkpoint 6, 000 selected by validation loss. A second answer-only, SFT baseline performs much worse, showing that memorizing answer strings is not enough. Online RL decisively beats both baselines. Trivia Q exact match jumps from 36, 5 to 63, 6 natural questions from 6, 0 to 18, 2 and hot pot Q from 7, 5 to 17, 0. Reasoning SFT improves modestly, so successful traces help, but online adaptation supplies most of the gain. Training happens only on Trivia QA, yet extracted recall also rises 4. 2 points on natural questions, 2, 1 on hot pot QA, and 0. 6 on simple QA. Strategy Q exact match rises 3 points. That breadth supports improved access rather than narrow answer memorization, though only one trained model is tested. The appendix makes the behavioral change concrete. The base model denies Canada had a woman prime minister. The RL model retrieves Kim Campbell. It also repairs Mexico's Manuel Morno Torres Dam and identifies Rudyard Kipling, sometimes after long association search and sometimes almost immediately. Average trivia Q thinking grows from 94 to 107 tokens after RL. But length is not the mechanism. In many corrected cases, the trained model simply states the right answer earlier, so improved calibration, better guessing, and better memory search remain difficult to separate. The token table reveals another pattern. Failed recalls are much longer than successful recalls. On Trivia QA, base successes average 41 thinking tokens, while failures average 174. After RL, those become 55 and 227. Longer search often signals that the memory was not found. Queuing the trained model produces a nuanced result. Extracted recall rises slightly, but exact match falls on every QA dataset and significantly on 3. So the claim that Qs still help after RL depends on the metric. More verbal searching can expose the answer while making the final string less exact. Trivia Q/RL unexpectedly improves unqueued math accuracy from 89 to 83. 9, while the queued score stays 84. The authors flag this as an opportunity for study, rather than evidence of a general reasoning upgrade. The strongest caveat is conceptual. Answer reward verifies outcomes, not thought quality. Only GPT open source 20B is trained on one source dataset. Strategy QA uses its training split, and extracted recall depends on a separate model. The study shows trainable access, not a complete theory of memory retrieval. Reasoning models can know more than their default behavior reveals. A 4-word Q exposes a small access deficit. Final answer reinforcement learning turns that deficit into large, transferable gains. But the resulting traces remind us to distinguish better recall from better explanations of recall.